All right. So we just said that the nucleus can also exist at discrete energy levels. And so I have an example here of americinium 241, and it can emit 3 different energies of alpha particles. Now, one of the things that happens when a parent nucleus, like americinium, I'll label this as a parent. Once it undergoes alpha decay, it has produced an alpha particle with a particular energy and a daughter nucleus. So when americinium undergoes alpha decay, it produces neptunium down here, neptunium 237. Okay, so this is the daughter. Okay, so the parent nucleus undergoes alpha decay. It emits an alpha particle. And each parent nucleus, when it emits an alpha particle, it emits alpha particles with discrete energies, right? They have distinct amounts of energies. Okay? And americinium can have an alpha particle emitted with 3 different distinct amounts of energy. Now, one thing that's been noticed during alpha particle release is that the daughter nucleus, after the alpha decay, it can be in an excited state. The nucleus itself can be in an excited state. And so if the parent americinium emits an alpha particle that has an energy of 5.433 mega electron volts, the daughter nucleus will be in an excited state. It would have a nuclear energy that is E2, right? Very similar to an electron in its second excited state. But this is a nucleus in an excited state. And nuclei, when they're in an excited state, they, just like electrons, want to return to their ground state. And so some energy has to be emitted, and it's emitted as a photon, right? Just like an electron making transitions would. Okay. We call this emission of photons by an excited nucleus. When it transitions down to a lower energy level, we call that gamma decay. All right. So if we know the energies of the alpha particles that are emitted from the parent nucleus, we can then infer the energy states that the daughter nucleus can have. All right. So if we follow this red line down, an alpha particle with this amount of energy, right, will produce a daughter nucleus in its second excited state. Okay, if we follow this blue line down, an alpha particle released or emitted with this amount of energy will result in a daughter nucleus in its first excited state. And then if an alpha particle is emitted from americinium with this amount of energy, then that daughter nucleus will actually be at its ground state, okay, and not actually excited. All right, so if I wanted to calculate the energy that a daughter nucleus has and the wavelength emitted by a gamma ray from the transition from energy level 2 to energy level 1, we'd be looking at this transition here. Can we calculate, right, the difference in energy between those excited states? And if that transition happens, how much or what would be the wavelength of that photon? Okay, so you literally, actually, we don't know the energy at E2 and E1, but we do know the amount of energy of the alpha particles that are released to get a nucleus to energy level 2 or energy level 1. right? So what we're actually going to do is, instead of knowing the absolute energy at either of these levels, we're going to take the energy that an alpha particle has when it decays to energy level 2, and we'll take the energy an alpha particle has when it decays to energy level 1. And even if we don't know how much energy there is at these levels, we know that the difference, right, the difference between these two levels is the difference in the energies of the alpha particles that are emitted. Okay, so delta E would be 3.486 minus 3.443 mega electron volts. Whoops, that's not how you write electron volts. And we would get delta E equals 0.043 mega electron volts, which is, remember, mega is times 10 to the 6. And so if we wanted to find how much energy was released, we just subtract the energies of the two alpha particles that were responsible for the decay to one of those specific energy levels. And then we set that delta E equals HF, but we're looking for the wavelength, so we want to do HC over lambda. And as a reminder, I'll write it over here. Planck's constant in electron volts is 4.136 times 10 to the negative 15 electron volt seconds. Okay, so we put our energy right here, Planck's in electron volts, Planck's constant in electron volts, the speed of light, and we can solve for the wavelength. And the wavelength turns out to be about 3 times 10 to the negative 11 meters. Okay, and then if you look on a graphic for the electromagnetic spectrum, we obviously know it's less than visible, but like where exactly is this ultraviolet, X-ray, what sort of thing? And it turns out, and this is confusing, you guys, this is confusing because what we're talking about here is called gamma decay, but there's also a gamma region of the electromagnetic spectrum. And so this gamma decay has produced a wavelength that's also happens to be in the gamma region of the electromagnetic spectrum. Okay. All right. Clear as mud. Cool. All right. So let's take a look at another one of these little infographic things. Gamma decay. This process is called gamma decay. And you can produce gamma rays. Generally gamma decay originates in a nucleus. Okay. Obviously, light has no mass. It has no charge. It can do whatever it wants. It can travel as far as it wants in air. And it indirectly ionizes. It's not directly interacting with elements. Okay, X-rays as photons can also be produced. And what happens is electrons can be spontaneously ejected from an atom, and then higher energy electrons in higher orbitals will pop down to that lower energy level and produce a photon in the X-ray region of the electromagnetic spectrum. Okay. And so obviously the energy level transition, the amount of energy is associated with the specific energy levels in between the orbitals for a specific element. Okay, so they'll be associated with the element. And then there's this funny type of photon. It's called Bremsstrahlung, and it's generated when charged particles decelerate, right? So we know if we wiggle an electron, it produces an electromagnetic wave, which is light. And so if we speed something up, like an electron, or slow it down, it'll produce light, and that's called bremsstrong. So those are the three ways that we can get some photons from an atom. All of light can be shielded, right, stopped with high Z materials, so high mass number materials. So we often think of things like metals, specifically lead, for shielding, like X-rays, right? We've worn lead vests to protect ourselves from X-rays at a doctor's office or dentist's office, for example. All right, so just to kind of summarize, right, we've talked about alpha, beta, and gamma decay from a nucleus. And let's just kind of summarize what this is. So remember, alpha particle is a helium nucleus. It's got positive 2 elementary charge, and it's pretty massive in comparison to an electron. It can only travel a few centimeters, but is very ionizing. So it can cause a lot of damage in the small distance that it can travel. It causes strong fluorescence. And so to detect it, you just have to send it through a fluorescent material, and it'll be very fluorescent. It affects photographic film. It can affect electric and magnetic fields, right? Beta particle is an electron, a little less massive, charge of -1 elementary charge, and it only travels a few can travel a few millimeters in metal, but is less ionizing, right? It also causes fluorescence and affects photographic film, and can affect electric and magnetic fields. A photon obviously has no mass or charge. It can go through many centimeters of lead sometimes, but is not very ionizing. It causes fluorescence, it affects photographic film, but it does not affect electric or magnetic fields. So I've got a little graphic for you. So alpha particles can be stopped by paper. Remember, they can also be stopped by skin. Beta particles can be stopped by plexiglass, also fabric, remember. And then gamma rays, they're just kind of slowed down by stuff. Most of them don't get through lead. Okay, so now I've got a quiz. This is a matching quiz. I want you to think for a minute about what you would do for each of these particles to protect yourself from each of the particles. So what would you do with alpha, beta, gamma decay? Would you throw it away, eat it, hold it in your hand, or put it in your pocket? And there's one correct answer associated with each type of decay. So take a moment and see what you can do. All right, let's see how you did. All right, remember, alpha particles are shielded by the skin, so you should hold it in your hand. Beta particles can be shielded by fabrics, so you could put that in your pocket. Gamma particles are shielded by high Z materials like metal, so you throw it away, put it in a metal trash can. And neutrons are not harmful at all, right? Go ahead and eat that. All right, so for your homework, on the Google Classroom, I've posted a activity about nuclear decay, and you can use 50 objects. This is intended to be done with 50 pennies, but you could use 50 M&Ms, 50 Skittles, any 50 things that are identical in mass and have a top and a bottom. And if you don't have access to 50 of anything, I do have some data preloaded for you that you can use to make your graph. All right, have a good week, you guys.